Yes. Great. Okay. Let's get going. So we have two presentations today by Tong Tao and Meng, and then we have this practical on chord recognition, which is also basically the foundation of the third and final mini project, which is officially set today and then due in 2 weeks from now. So we'll be able to talk about that after the presentations. Any other points before we get started? Anything? Okay, so let's just come up. So.
Thanks.
All right.
Hello everyone, my name is Tong Tao Zhang. My topic today is Markov model in music. This is my outline. First, I will take a quick intro to Markov chain. Then I will give you a very simple model, Markov model, and show that what will be applied in music processing. And also, I will introduce algorithmic music composition. To conclude the presentation, I will give you a summary and tell you about more about the future work. So first, I will give a fast intro to Markov chain. So the definition of Markov chain is here. So it's a very long and boring mathematical formula. Then I will give you an explanation. So what is Markov chain? The probability of x equals to 1 or 0 only depends on what it was, or what the previous symbol is, only depends on this. And nothing deal with this and nothing about this. Then, so how to express Markov chain? Here is like the transition matrix. I have a series of symbols here. Then I will calculate how many zeros followed by another 0, or how many zeros followed by another 1. And also I will do the same thing to 1. And I will calculate like this. There's only 1 0 followed by another 0. And that's just 1. Then I will normalize the row. Then I will have a matrix like this, only this. And also I can denote the transition matrix like this. So this is 0, this is state 1, and there's 1/6 probability to stay in 0. And like this. And so 5/13 probability here. And 5/8/13. Like this. And then I will combine my idea with the music. Let's take a very simple example, like the Little Stars or alphabet song. Do, do, so, so, la, la, so, fa, fa, mi, mi, re, re, do, like this. So I will calculate how many C4 followed by another C4, or G4 followed by G4. And then I will have a table like this and count then normalize the rows, have this. Then I will do something visualized. I put it in the MATLAB and show the probability like this, make it more, to say, obvious. Then what about applications? I will tell you two parts. One is music classification or recognition. The second is music composition. So first, like the transition matrix can tell us where the music comes from. For example, you can combine your cultural background. Like Chinese traditional melody never contains F's or B's. That is Fa or C. I'll show you one. So here is the transition matrix table. So, but in my script, I just omit the zeros, all the zeros, so you cannot see a C#5 or like the F. So I will do an illustration here. Here you can notice that I have already written down the numbers and the corresponding notes here. So you can notice that. So we start with 69 or something, and then we can say we don't have 77 as here. We don't have anything starts with 77 or jumps into 77, and nothing about 83. So here, about here, nothing starts with, nothing jumps into, and also no 89. Sorry? Oh, F5. There's some noise or? Okay, sorry, I don't know. Is there anything wrong with that? But just for most Chinese traditional melody, we don't have F and Bs. And also, the Markov matrix, a transition matrix can tell us what the music says. For example, happy, sorrow, or encouraging. Like let's listen to a happy music. So we can notice that for this kind of childish or happy music, we can see that the points are just like distributed scatter here. So there are very few like transition. So most are distributed along the diagonal, but there are very few. Just we jump very very big range. So let's listen to a very sorrow music like this. Okay, so we can notice that there are some notes jump from very high to very low here. So that shows that there is like sorrow or not a happy meaning. What? For this means from 85 to 73. Do you notice that? From 85 to 73. Sorry, here. Just from a very high jump to a very low. Yeah.
How do you get the law for number changing some of the one?
What? It's just a very simple model, just an example. And I will tell you later more about that. Then some like encouraging, like this. So that is the Chinese army marching across Tiananmen Square. So, like this, for this kind of music, we can see there's some high frequency of note patterns here. They just appear very often. But actually, what I give you is just a very simple model. So actually, there are many complicated issues. So we need more accurate but more complicated models, such as hidden Markov model or the second state Markov chain. And this will be included in our future final project. This might be used. And also other instruments will influence the expression of the music. Like if I add some drums in the music, it will be here sounds like it's very encouraging, or like that. And also for same piece of music, it sounds different to listeners if you have different cultural backgrounds. I think for people who don't live in mainland China, have never heard of the previous four melodies. So this might cause some different feelings to you. So how to solve the problem? So I can distribute the MIDI files to you, and you can make a vote. Then I will take the statistical results to establish my training set if I want to make the music classification. So for the final part, I will give you something more interesting. So you can compose a piece of music on your own. So you have the transition matrix. So you can start with a certain note. Then according to the probability, you can decide which is the next note is. So I will give you a demo. So this is original music. So then I put the music in the MATLAB here. Then so it will be, although sometimes it does not listen so good, but so wait a minute, I will do another. Pardon?
Yeah. All the song that we just did, you just retain the initial spacing between the notes, right?
Yeah.
From the initial song. And also, how about the two voices? Did you extract them together so that every...
I know there's some like on the keyboard, there are two keys just pressed for the same time. Yes.
Yeah.
Yes. I just use a very simple model.
Okay.
Just I don't care about, for example, the two notes are running together. I just according to the reps in the MIDI file and just calculate the matrix. So do another. So it sounds a little different, and okay. Then jump back. So just at last I'll give a summary. So Markov chain. Markov models can be applied in music classification, but I will give you more details in my final project. So, and also you can compose your own music. So if you are really interested in this, I think some software can be recommended, like C Sound or Max or Super Collider. That's it.
Thank you.
Yeah.
Any questions?
Yeah. Okay.
So, I'm not sure how much information conveys this transitional matrix in terms of, sadness or sorrowness or happiness, etc. Because it seems to me like just discerning what sort of mode the song is written in. Like, for example, saying that it's C major or minor
Yes,
or
I
whatever.
also know that I just omit the chords, also omit the rhythm or the time lasting for each note. So if I take the little stars, there's another expression for here. So you can, I think you are always familiar with do, so, la, la, so. So actually, in some models, you can just for this so you can split into two sources here. I just use a very simple model in the presentation, but for future talk, I will do more complicated, like the second Markov chain or other second stage. So second order, I will calculate how many C4 followed by C4.
Okay, so two memory.
Yes, to go to memory to make it more complicated and more accurate. Okay.
So, but in the synthesizer, in the new versions you created, there was rhythm and stuff like this. So where did that
Yeah, because I just directly put it back to the MIDI file, because the MIDI file also contains the rhythms.
Only the
So you
notes
rewrite-
are-
you
So
rewrite
I
the-
only just change the notes.
Gotcha.
Yes, I just want to make my MATLAB script more easier to.
I still still don't understand how I managed to get the baseline in the right. You know, say the simultaneous notes. I guess if that was written as a separate track, it would be files.
Yeah, maybe.
It sounded right. But it's not the point.
Another assumption is that the longer the song becomes, the bigger the number of transitions there are going to be. So I think that if you try to do the same approach with longer songs, maybe it won't work that well. And also how about songs that change the melody in the middle, they change the mode. So this is going to be too much useless information. One part applies to the rest.
So this is where like the statistical results. I will just will convey like you vote the music. So maybe I will just cut the music, cut the happy part or cut the sorrow part. Just I will just make sometimes make one piece of music more accurate with the latter.
No, what I just mean is that maybe you should also incorporate some sort of forgetting mechanism. So that you should retain this Markov matrix and just update it every 5 or every 10 notes, so that you don't remember a lot of stuff that happened in the past in the beginning of the song.
So did I hear you correctly that you're going to get us to you want us to provide ground truth ratings of the emotions of this music? I think that's a very. So the problem is, like, you say, well, this is a happy song, and it's because of these structures in the transition matrix. Well, show me the transition matrix in a happy song and a sad song. There are differences between them, but does that mean that these differences actually are about that aspect of what's different? Because they're different songs. They of course have different transition matrices. So the way to do that is to try and build some kind of classifier and show that it generalizes. But the problem is getting data where we agree what the actual correct label is. I think it's a great idea, but there's some work involved.
So I'll take them into account.
All right. Great. Thank you very much. That was very nice. So that was also very good timing because we're going to be doing Markov models for the practical today. So that's a nice additional introduction that we can draw on. Okay. So and now we have Ming, right? Do you need audio?
Yeah. How can I change the resolution?
Yeah. Try changing it back if you go to the control panel.
Hello everybody. Today I'm gonna Today I'm gonna give a short present about what I have done in previous 2 mini projects. So it's going to be quite simple. For the project one, it's a simple implementation of the finished guys paper, and I'm gonna give you the basic theory behind the 2 simple methods: the threshold and the polyphony estimation. Finally, I give the results demo and a comparison. So basically, the paper is actually treats the musical mixture of different instruments. So it's like, because it's different instruments, then the fundamental frequency is like kind of tends to be continuous because there's a lot of instruments. But in our case, it's gonna be much easier because we are only dealing with the piano with 88 keys of discrete frequencies. So the basic theory behind the paper I have been used for the project one is quite just use the so-called the salience function as a polyphonic pitch estimator. So as you can see, it's like there's some fact over here. So this S is actually the salience function, and you can have the wave function. This is some kind of I don't know how it comes out, just called the paper. And this is the actual spectrum transfer from the continuous domain to the discrete domain. And the F we need to transfer from analog to the digital, and basically the thing about it is like the harmonic factors is like M is the harmonic factor, and as you can see, maybe you have experience like actually the maximum value of some kind of harmonics modules is not exactly decided at the modules. So we need a kind of range to get the actual maximum value. That's kind of small range. So we try to have an integer set which contain all the ranges about these harmonics, what kind of data we want to search for the maximum value. So this is the upper limit, and this is the down limit. All the integers in between are going to be tried to find the maximum value to represent that harmonic. And the 2 methods, one is threshold. The threshold is very simple. It's just normalize the 88 salience function and set a threshold. It's like the value is kind of experimental value, so it's 0.9 here. And for the second method, the polyphony estimation, in a nutshell, it's gonna estimate the number of fundamental frequencies in the mixture. The difference in about compared to the first threshold. About first, we just set a threshold, so we can know how many fundamental frequencies we actually have at this moment. And for the second one, we have this formula at the end, at the bottom of the slide. Try to guess how many fundamental frequencies we try to extract right now, because we are doing the poly. So I'm gonna show you shortly about how it works out. So I think the purple line is actually the poly, I guess. Let me see. Yeah, I think the blue one is the polyphony estimation result. And also you can see and the green line actually is the original one given by the professor. Use the maximum energy or something, and so we can see the difference by, and also we can try to look at the threshold method. But the weird thing about it it seems like the threshold method is kind of kind of same, but there's still some minor difference. And also I give you a feel about the single pitch, so you can see the difference between the multiple pitch simultaneously and the single pitch. So I guess this is the wait. I'm not that familiar. So this is the single pitch. As you can see, at each moment, there's only one pitch gonna be detected, and for the polyphony, you can see there at the same time, there gonna be several pitches gonna be detected at the same time. So, but I haven't been doing the evaluation of the performance yet. So basically, that's it. Then I'm gonna talk about the second one. So for the second one is a simple implementation of the mirrors method. The procedure goes like, for the first step, I'm going to do the single node sum extraction using the sphere. And for the second step, it's going to do the envelope polynomial interpolation in MATLAB. And then output the data into a text file, and you can do the file into the PD and do the time invariant fixed spectrum sinusoid synthesis. And after that, I'm going to add two additional components, the ADSR and the LFO. So this is the sphere. The sphere, I set the spectrum of the frequency to 20 Hertz. So that's going to be quite enough for differentiated at A5. I think that's enough. So because the sample, the nodes given by professor is actually not that, it's not go as low as A5 actually. So as you can see, actually it's quite clear here. It's like we have many feasible and we can easily see the that's quite many single nodes we can try to get data and see what kind of amplitude at what kind of frequency or pitch. So to better have the feel about what kind of frequency actually we try to get, we can compare with the score. And the funny thing about it is that you can see the configuration is quite similar. Here it's like, you see, and it's go down and it's like this. It's like this. So it's quite similar. You can just simply get, you can compare here to try to check what kind of frequency and you see. Because there's some place maybe you are confused and you don't know what fundamental frequency actually it is. Especially for me, I know almost nothing about music, so I needed to use the score, try to figure out what kind of fundamental frequency it is. And this is the result, pretty much the result of envelope interpolation. I think if you extract more data, you're gonna make the shape better. So, and actually for the graph here, I already take out there's some data which is really out of sync, so I take it out and then I manually take out there's some point which is really out of the area and do the simple polynomial. It's not that complicated, just a function in MATLAB. And we're gonna see it in PD. So I left the implementation over here. So my implementation is over here. Actually, I have several files. One is like the load envelope file. It actually gonna load the interpolation result into the PD, and I load at the MIDI numbers, not at the frequencies in terms of in the x-axis. So I think not too much to see here. It's like just a simple copy of of another version, and we try to get the envelope. Let's file. Maybe you can take a look. This actually is a file generated by MATLAB, so it's going to be from the MIDI number 70 to 120, and at what kind of MIDI number and what kind of amplitude we actually get from the interpolation, and we release kind of data into the PD, and in PD which we have the read for object which can do the kind of interpolation to get what kind of value at the decimal in between the integers. And here is just a simple ADSR, try to control what kind of, I'm gonna set a value here. This is all, the unit is millisecond. And I add this FFO component, which have some kind of effect when you're hearing it, but I don't think it works very out. And I'm gonna have the score. I think that's one thing different from the previous implementation given by professors. Like actually in the previous one, for every note, only gonna be played for 60, 50, I guess. The 50, maybe 60, 50, I think it's like 160, 100 millisecond for every note. You actually don't use the information of the duration. So I try to use the information of the duration here, and here's a. So you can hear some kind of vibration during each note. That's because they are LFO, and but the effect of ADSR maybe is not that easy to hear. The effect about ADSR, and but that's the result that pretty much I get. Not that. Okay, so I think that's it. So do you have some question?
Okay, questions for me? On the first one, on the BlackBerry model, you
mean the Projo one?
Yeah.
Okay.
So your implementation had like 4 different systems. Were they all? I mean, it seems like the BlackBerry thing was a lot more complicated than the others.
Yeah, of course. It's just a simplified version about,
Right.
Because it's actually doing the differentiation and try to get what kind of because it's like the mixture of the instruments. It's a lot difficult than our versions. My version is only for piano, so that's much things simplified.
Does it? Could you see that it was doing better? Or
that's one thing is really bothering me. Is like I don't know how to do the evaluation of the performance. By hearing, I didn't get the score. I didn't get a score for the sound. Without the score, I even don't read the score. I can't read the score. And when I listen to music, I don't know what kind of pitch. So it's kind of, I don't know. Just the performance I guess is like that, but I couldn't do the evaluation yet. I maybe need some professional who can listen to it and see whether the result is correct, I guess.
yeah, it'd be better to do it.
Yeah, okay.
Computer do it rather than having to get a person to do it. Yeah, it's not true. Just because we don't have the right, we don't necessarily have the ground truth. I think the actual example is synthesized from MIDI, so it should be ground truth.
Mhm.
And for the synthesis one, each note. So you have this table, which is the average, the interpolated energy of the notes at different frequencies, right?
Mm-hmm.
And then you get a particular note that comes along. So what you figure out its harmonics, and then you get its amplitude by looking up in that table.
Mm-hmm.
Is that what you do? So
Yeah.
all the nice, and then that gives you the variation in energy and frequency, and then you do the ADSR to get variation in energy and time.
Yeah, but I think that's one concern about the fixed spectrum, is that it's like because the code given by you, actually you are doing for each single note you try to, for every you play the note at 160 millisecond, and that's actually 16 samples, and each take 10 millisecond. So it's like a time variant is actually. I mean the amplitude of the frequency is time variant. So I try to mimic this at ADSR, but I don't think it works out well. And so I think that the problem is like we have the fixed spectrum here over time. So why do the spear extraction for the data? I try to actually it's like, for example, for this one, I guess the data you get is like from the beginning to the end. It's like it's 2 weeks to join on the 2 weeks. That's the data you use. And the data I'm using is only the middle one, the strongest one, and I use the ADSR. But I think the finally the outcome is not as good as used version. I don't know why. And
I don't think there's that much difference actually.
Okay.
I think it's quite well. What you did was well motivated because it sounds similar, and it gives you the opportunity to parametrically vary the duration of the notes. If I'm just using the exact amplitudes of the things, then it's like, well, what do I do if it's a longer note? I've run out of amplitude values, so I can't make them longer. But once you have the ADSR, then you can make some general. But I guess there's the question of how you set the ADSR values.
yeah, I also not that sure how should I set the ADSR. So.
Sort of want them to match the
You
actual
know,
data.
The thing is like for the instrument, you like the piano, you're doing the plug or the bow, you have some kind of different ADSR setting. But it's like you are singing the song, you don't know what kind of ADSR value you should set about it. And also for different durations, what kind of ADSR you should set about it. So that's kind of tricky thing.
Great. Any other questions? All right. Thank you very much. Those look like really nice. Yes, this is the project.
Thank you.
And thank you for taking the time to explain it. Okay. So what we have now is some stuff on chord recognition, and this is following on from what I presented on Monday. And it's also, like I said, it ties in nicely with the first presentation, the Tongtao's presentation, because we're going to be using Markov models. And so, now we're working in MATLAB. And so, but what I've put together here is, just turn on the sharing here, is a very small, fairly simple set of code and some data, but it will allow you to actually do chord recognition. So let me just quickly walk you through it, and then you can try it for yourselves. So there are two zip files here. One contains the code, a bunch of MATLAB functions, and the other contains the data, which is sorry. Let me just show you what you get. So you download these, you get this folder with code, and then I drop the data you get a folder with data which you put inside the code folder. So the data it's actually the entire corpus of the Beatles, but analyzed into these beat synchronous chroma features that we talked about. So I've already run this on the audio, generated done beat tracking on every track, and then for every beat length segment extracted the chroma for every track. So we have the chroma features, then we also have the labels, and these are they're in map file format, but they're the ground truth labels from Chris Hart, this guy at the University of London, on the same beat segment. So I've taken my beats, figured out how they align to his labels, and then you've got a bunch of corresponding labels. So what you can do, you can use load chroma to load one of these chroma feature files, and that just gives you a 12 by number of beats, 12 by 500 array. You can use synthesized chroma to regenerate an audio file that just does the shepherd tone things that we heard on Monday. So it'll generate something which is a version of what the chroma file heard, which you can listen to. That's what the data is. But then this trained chord models is just building a simple Markov model with Gaussian emissions. So what we do is we have this data, we just have a list of files. We load, for every file, we load the chroma features and we load the labels, and then we just stick them all together. So then we end up with this very long set of chroma features of, 10,000 frames or more than that, by 12 chromas. And then a corresponding vector of labels, 10,000 elements long. For each frame, it's an integer label between 0 and 24, where 0 means no chord, 1 to 12 means C major through B major, and 13 to 24 means C minor through B minor, something like that. And so then what it does, it basically for each model, and there were 25 models, the no chord and the two sets of 12, it finds all the frames in the label vector which have that label. And then, assuming that we've got more than 0 of them, it works out the mean and the covariance of all the corresponding chroma frames, which then gives us a single Gaussian model in chroma space, in 12-dimensional chroma space, of what beat whose label is that label, what its chroma features look like. So basically, we build 25 of these models. If there are no labels, it just reverts to the global mean and covariance. But I think there are actually instances of every one of these 25 chords in the data set. This is the emission part of the Markov model. That is what we see, what comes out of what we see in the observations for this particular label. And then we also have the transition matrix, which is the thing that Tong Tao was talking about. And what we do here is we look at every pair of labels, and so I convert every transition into a single number, so that it's like a sequence of numbers where it's 100 times the first label and 1 times the second label. And then for each of those labels, I just count how many times a particular transition occurs in a transition matrix. That gives me this transition matrix. I also calculate the prior probabilities, how many times each chord occurs in the whole data set. But that's our Markov model. It's the transition matrix. The outputs here are the transition matrix, the prior probabilities, which is just like what the probability for the first chord if you've got no previous chord. And then the models, which is just this set of Gaussians, this a mean and covariance in 12-dimensional space for each possible chord. Oops. So that's as you see, it's pretty straightforward to build those models. And then what we can do is, for a given set of chroma features, we can use the models for recognition. And this is very simple because we're using a couple of functions which were written by Kevin Murphy in this HMM toolbox. We just have one thing which calculates the probability of each model for each frame, which then gives us, we start off with a set of frames of 12-dimensional chroma vectors. After we pass them through this, we put those 12-dimensional chroma vectors and these 25 models in. And now we get out a set of 25 posterior probabilities for each frame, which is likelihoods, how likely they are under each of these 25 models. And then with that set of likelihoods, we just do this Viterbi path, which does the dynamic programming thing of finding the most likely sequence of labels given these local models and given the transition probabilities. And that's pretty much it. And then we can compare those recognized labels with the ground truth labels and get an accuracy. And then we can do that's for one track. We can do that we have a little thing here which calculates a confusion matrix, which you can do. We can resynthesize chroma from the actual labels, which is kind of just the simplified form, just to see what it sounds like. We can plot the comparison of the sort of ideal chroma, the actual recognized chroma, and then the true and the recognized labels here for a particular track. That's what this graph up here does. But then we can just run this over an entire set of tracks to get an overall accuracy, not on just one track, but on an entire test set. So you can run all that, and so you see it's pretty straightforward. In particular, the building of the model is just finding the right subsets of data, because we've got labeled data and calculating its mean and covariance, and then calculating the transition matrix. And recognition is just calculating the likelihood under each model and doing the Viterbi path dynamic programming, which we don't have to worry about how that is calculated. And so now we can do things like changing the training set to see how the performance depends on how many tracks we use with the training set. In general, more training data leads to better performance. We can look at how much variation there is in the performance of individual tracks, which is kind of interesting. So you can, for instance, find the single track that has the worst performance at recognition time, and then you might know that track, and you might be able to say something about why it's a bad track, why it's a difficult track to recognize. You can listen to the resynthesis of the errorful transcripts, because then it's like, well, all the error just tells you, well, it was the wrong chord label. But it doesn't tell you whether it was completely wrong or whether it was like a sort of arguably plausible. If you listen to the resynthesis, you can sort of hear, okay, does this sound like the real chord sequence? And then there are things you can do with the features. So there's actually some feature normalization involved in the load chroma routine. If you look at it up here, it reads back these raw chroma features, but then it finds the maximum value across the entire vector, and it just divides every column by the maximum value, so it normalizes the values so they have a maximum of 1 in each column. But there's this thing I commented out here which does a compresses the values by raising them to the 1/4 power before doing this, and that actually helps. So you can try that with and without that normalization. And then there's the transition matrix, okay? Here I've just taken the empirical transition matrix, which is, I've counted the number of transitions of each type across the entire data set. But you could put any transition matrix in there. You could say it's got a uniform probability going to any other chord, which would be just having it be the transition matrix be a constant set of constant values. Or you could say it's most likely to stay in the same chord that has a small probability of going to any other chord, which would be this plus some leading diagonal. And you can see how that affects the accuracy. That's basically how much smoothing the hidden Markov model is doing. And it's 11:52. Why don't you just have a go at deciding this? So, and bear in mind, the assignment, the third mini project here, is just to carry on doing this, and then seeing how well what you can do to improve or investigate these different things. So we can have a quick look at this now, but then you can carry on doing this over the next 2 weeks for your mini project. Any questions about that? Okay, so let's spend 15 minutes just see if you can get this going, see if you can try some stuff out, and then we'll talk about anything that we observe coming out of this.
the it's 25 or 25 matrix, right? 25 matrix. So it's 25 states in our Markov model.
Transition is from one chord to another chord.
Yes.
But Gaussian model is for each chord will have one Gaussian model.
Right. So this is the difference. This is why it's not just a Markov model, it's a hidden Markov model. So we understood from today's presentation before, the idea of a Markov model is you've got a particular state at a particular time, which in this case, for what we're doing now, is a chord, like C major, C minor, whatever. And then it's a particular beat, we're in a particular chord, and then the next beat we're going to be a different chord. The Markov model says, well, the probability of which chord you're going to go to, it's not random, but it only depends on what chord you're in now. So if you're in C major, it turns out the most likely thing is the next beat you're going to stay in C major, but you might go to G major. So that's the state sequence, but of course we can actually get the state sequences by getting somebody to go and label what they think the chords are. When we have a new piece of music, we don't have the state sequences. All we have is the feature observations. So that's the idea of a hidden Markov model, is that there is some Markov state sequence there, but it's not directly observable. All you have is some features, and features also depend on the current state, right? So they also, what you expect the features to do have this Markov property that they only depend on what the current state is. That's all you need to know. But they depend probabilistically, so you don't get the straight answer. So what we have is, for every chord, we have a PDF, a distribution of what we think the features are going to be, and that's represented as Gaussian in the 12 dimensional.
The first level is the transition matrix. The second level is each chord will have a Gaussian distribution.
Exactly. And we get that by looking at all the frames that have that label and just calculating the unit covariance, which is basically this oriented Gaussian blob of 12-dimensional space. And then if you give me a new frame, I've got these 25 blobs in feature space. I can calculate the likelihood of that frame under each of those blobs, and then that's like, well, if you just tell me that, just give me this one feature frame, it's more likely to be C major than to be D major. But if you just do, so then you can do that. So
the Gaussian model is just to compute the likelihood of any given set of which chord most likely to under.
yes, that's all it's for, but that's like the whole thing. That's kind of like, but maybe, okay, let me show you what I did here. So previously, in the script that at the beginning of the class, we just did the recognition of chords, and then we just did the evaluation of the independent string chords. Now I've put a texture block in here, which actually looks at, I changed the function recognized chords. Reload it now. It now outputs the likelihoods as well as the labels. And which is just this thing we were already calculating. So now having come out of the function. So now what we can do, so let's go to that. So we train the models, and then we do recognize chords, which takes the Chroma feature of the observation, the Chroma observations, the set of models, the Gaussians, and then the transitions and the priors, which is finally the hidden Markov one, the Markov one. It asks us the outputs, the hypothesized chord, which is 555 frames, right? Which just labels what it gets. The same starts with the C major and goes to whatever the G major is, G major is. But it also outputs these likelihoods, which for each of the 25 beats outputs the likelihood of each particular model. So if we plot that, we get this. So it's got, these are time frames, these are the 25 models, and this is the notable model, these are the 12 major models and the 12 minor models. And these are likelihoods. And likelihoods vary over a very wide range. Because these Gaussians, when you have a density of Gaussian in a high dimensional space, it's the product of the Gaussian of each individual dimension, roughly. So now it's some number roughly raised to the 12th power. So it's going to, they vary over a huge range. So it's difficult to look at them. So I want to look at the logs. So log is 10. Again, it's still vary over a huge range. Now they're all pressed up here, but they also get very, very small. So it's huge negative minimum down here because it's the level 17, which is always the data. So now we're going to clip this. So we're going to look at the likelihood, but only if it's larger than, say, minus 10, which is still a huge range, right? A log 10 range from minus 10 to 3. So it's like from 10 to minus 10 to 1,000. Now we begin to see some structure. And let's zoom in a little bit. Okay, so this is like 25 chord models, each beat, and then showing the likelihood black is more likely. So this is saying, yes, the first 4 beats, C major is quite likely, but so is 8, which is G major. So is 14, which is C minor. So they're all a bunch of models which are quite likely. So we could just do this thing of saying max alpha. We just take the largest so this is, I don't know if you can see that, but this is now, here's the matrix of likelihoods, and then the little O shows the largest value in each column. Right? So this is just saying, forget about the Markov transition. I've got these models, I've got the independent chords, and then independently look at each feature vector, decide which model looks best. And that'll be my chord label. It does pretty well. It turns out, well, C is the best fitting for the first 4 beats, and then G, which are actually the right answers. But it jumps around a lot. So if I actually look at the if I try and, so I've got my ground truth. Truth chords, right? So I can load the ground truth with this thing, and I can find how often the true chord is actually equal to the thing I got here. True chords go from 0 to track 1. But that gives me this. So that gives me 44.8% correct. Whereas if I do my actual Viterbi path, which was the height chords, I get 71.5% correct. So the difference here I also plot the height chords on this graph. Let me just say, what the maxima, and then what the hypothesize the Viterbi path. What we see is where we had these maxima here that were like what turned out for 1 beat. C major was also the best fitting here. When I applied the Viterbi, the constraint, the Markov constraint, it says, well, you really want to, because the transition matrix says you most likely stay in the same chord, frame after frame. The actual, under the Markov model, the chance of going that single chord with 1 beat is very low. In fact, once you've got into this, whatever it is, B minor, it says, you might as well stay here because the likelihoods are not that bad, but we don't have to incur the low probability of transition. And so it tends to smooth out these chord trajectories and helps a lot in this case. So that's the difference between just having an independent classification of every frame and doing the Markov model to get this smoothing through time with this transition matrix. And it's a big, for this particular case, it's a big deal. We get a much better probability, much higher accuracy. All right, so that's hopefully given you an idea of what this is about. Any questions? Anything else anyone wants to remark on or observe? Okay, well, you're going to get plenty of time to look at this